So I'm here to tell a related story to the one that's related to the previous two stories. The problem relates to connections between columns and foundations. And the problem could apply to precast construction. It might apply to cast in place construction. We're still looking into that question with some colleagues elsewhere. But mainly this was a question that was asked by engineers designing steel buildings that were connected to concrete foundations. And so the real problem became one of column to foundation connections with cast in place headed anchors, and they're really anchor bolts. And so this is work that is being done primarily by a doctoral student at UC Berkeley, Ben Worsfold. One of the advantages of being virtual is that we get a nice audience on a Sunday. The disadvantage is I can't introduce Ben, but I know Ben is out there listening in to the presentation today. So let's get started with some of the detail in this presentation. Let's see. All right, so the foundation, the connection that we were interested in is the one shown at the left. And we've been doing some work related to connections that are subjected to tension and compression with similar geometries. Today, I'll only talk about the case where there is a moment connection. And the detail of the connection, we've got a footing that has reinforcement top and bottom. There is a steel column that has no axial load, transferring only moment in one direction. Very stiff base plate, and the moment is transferred into the connection through a set of 8 anchor bolts, 4 on each side, 4 in tension and 4 on the compression side. And the transfer really occurs through oversized nuts that are located at the bottom of the anchor bolts at about the same elevation as the bottom layer of foundation reinforcement. Of course, when this connection is subjected to pure moment, the tension and compression couple is the one that we see on the right. And the question then becomes one of, well, how do we address the design of this kind of a connection? In the ACI building code, the only obvious way of addressing this would be through breakout equations that are available in the chapter on anchoring to concrete. But many engineers responsible for the design of steel buildings have not been very happy with the results that they're obtaining from Chapter 17 of the ACI building code. The development lengths or the anchorage lengths are just so much bigger than what they used to be. Many engineers feel that the design requirements are a little unfair because if they were simply to replace the anchor bolts with hooked or headed bars, all they would need to do is to provide a development length for those bars and they could walk away from the problem. And the lengths would be far less than what's required when using the anchoring to concrete provisions. Many creative engineers have looked at this problem and tried to solve it in different ways. One of the popular ways of resolving this is to consider the joint, the connection as being one like a beam column connection. And if this is treated as a beam column connection, then we carry the force through a diagonal strut across the joint. And we provide some transverse steel to confine that joint. And we should be able to use the joint shear strength equations that are in the ACI building code or in Committee 352 to solve the problem. And then suddenly a anchor length problem that was extraordinarily large becomes more tractable. The design's much more efficient, and this has been a solution that's been used by many engineers designing steel buildings. But My good friend John Silva, who's going to be the next presenter, says, well, that's all fine and good. He says, but what about this breakout failure that might still occur? And so that was a basic question that drove the experiments, is if we design the connection to be satisfactory in accordance with the beam column joint provisions that we have in our code, why do we need to check the breakout failure, or do we need to check it? So that was a main objective in the experiments. Now, one of the reasons to think that maybe the breakout failure is not something that we need to think about is contained in ACI 31819, where it's suggested that if you have a beam framing into a column and the embedment depth of your anchor for a headed bar is at least the depth of the beam divided by 1.5, then you really don't need to worry about the breakout failure. And it suggests that the breakout failure is not going to govern the behavior. So we wanted to design a connection that met this development length for the anchor bolts by a good margin, so we could test out this provision. And in our case, of course, we're dealing with a connection that's flipped, and it's a column that is connecting into the foundation instead. The first test specimen that we looked at is the one shown here. It's a full-scale specimen. That silhouette on the right is me before the pandemic. Anyway, the connection full scale, the thickness of the concrete element representing the foundation is 18 inches. The connection or the foundation was not supported on soil. We wanted to simplify the problem somewhat, and so we supported the slab representing the foundation on a pad at the left and a pad at the right, and pre-stressed the connection down to the strong floor in the laboratory, and had air between the specimen and the lab floor so that there wouldn't be any interference in the failure modes that develop. The lateral load was applied up at the top of a steel wide flange section that was connected into a base plate with a shear lug at the base. The base plate was grouted to the concrete footing, and then 1.5 inch diameter anchor bolts with oversized nuts were used in the connection. Because we were thinking about this connection in terms of it representing a beam column joint, we provided hoops around the anchor bolts as would be required by ACI 318 or Committee 352 for earthquake resisting beam column connections. The slab itself, representing the foundation element, was designed to have adequate strength using grade 60 steel, but as an extra measure to make sure we didn't get local yielding, we replaced the grade 60 steel with grade 100 reinforcement. When we compared the strengths for breakout versus the strength that we would obtain from beam column joints, we noticed there was indeed quite a difference. And that difference really reflects the difference in length that would be required if, in fact, we were to design this connection using the breakout requirements of Chapter 17. Now, there's one thing I do need to point out with regard to the breakout strengths. In addition to the fact that we assumed that these were anchor bolts in pre-cracked concrete, the Chapter 17 provisions are based on a 5 percentile or 5% fractile of fracture for the connections. And most of the development length equations and other equations that are in our codes are really based on a 50% or median strength. And so what we wanted to do was to adjust the 5 percentile value up to the expected median value and used a factor of 1.33 to obtain that. So this is one of the challenges of using the anchoring to concrete provisions in our code. If you apply them to the design of foundation elements or other large structural elements, those provisions are based on a 5 percentile number for strength, as opposed to a median value. And so you've got immediately an inconsistency in the philosophy of the design strength definition. The specimen in the laboratory is shown in this slide here. I think I've got a video that will show how the test was run. The loading was applied cyclically. And now I can't get the video to operate. Well, we'll survive without the video today. And instead go to the next slide, which shows the type of failure that we did observe in the test. So after cycling back and forth, we did eventually get failures, and it turned out that the failures were indeed breakout failures. And so when we loaded in one direction, pushing the column from right toward left, we got a breakout cone that extended around the tension side of the foundation element, the slab. The extent of the breakout, of course, was constrained by the existence of flexural compression that comes into the base plate at the other end of the so-called joint in this connection. And there was a similar observation that Rolf Elegehausen showed in his presentation. For loading in the other direction, we also got a breakout failure. So the strength, again, was controlled by breakout in the connection. When we compare the various capacities that were obtained from the tests versus the breakout strengths or the beam column joint strengths, the breakout strengths are shown in the two right-hand bars, the blue colored ones. We had 240 kip as the anchor group load for loading in one direction and 266 kips in the other direction. Far less than the strength that would have been estimated or obtained by the beam column joint connection value, but also somewhat larger than the median predictor that we had for the breakout failure. One of the reasons for the difference between the breakout strengths as calculated and as measured, Rolf already mentioned in his presentation, but we'll show that again here, is the fact that when you have a relatively deep anchor in a moment transfer condition and the flexural compression force is acting fairly close to where the tension force is applied, that compressive force interferes with the development of the full breakout cone and constrains the failure cone to essentially follow the cursor, as I'm showing here, so that it ends up inside the centroid of the flexural compression force. This affects the strength of the connection, and there has been some recommendations on adding yet another C factor, C sub M, as Rolf mentioned in his talk. There have been various proposals for what the value of this factor should be, but generally folks have considered that the value of this additional strength modification factor for breakout failure should vary with the horizontal distance from the tension force to the compression force divided by the effective depth of the connection. And we also would recommend, as Rolf did in his presentation, that it's time that this factor is probably considered for addition into the ACI 318 code for at least these kinds of applications. We also began to study this problem using finite element models. We used the Athena software. One of the reasons for pursuing this, in addition to gaining a better understanding of the fundamental aspects of behavior, was because these connection tests are really very expensive to run at full scale. And we wanted to explore options for additional tests analytically before moving forward with physical experiments. So we Ben developed finite element models that were calibrated with single and group anchor tests. Once we had pretty good results in comparing analytical and experimental results for the single and group anchor tests, we moved on to developing full models of the column to footing connection. And you can see here the mesh sizes, how different details were put together for the interface between the plate and the concrete modeling of the anchors. We mostly ran monotonic loading. The cyclic loading results were took longer by computer by far than they took in the laboratory. And then looked at various modeling formulations to finally come up with a model that we felt was best in terms of its predictive abilities. This slide compares results of the best finite element models that we put together for the cyclic test of the connection that I just presented. So excellent results in terms of stiffness and in terms of the strength, and additionally the failure deformation seems to be roughly in accord with what we got in the experiments. One of the reasons that we pursued this, as I mentioned, is that we wanted to explore options for modifying the design and improving the strength of the connection without actually making the anchor bolt length longer. And so one of the solutions that we came up with was to try shear reinforcement. And the shear reinforcement was used in the form of what we call a candy cane bar. This kind of detail is fairly commonly used in thick foundation elements on the west coast of the United States. It's pretty easy to apply. You insert the headed end into your reinforcement cage, hang the top end off one of your longitudinal bars for the mat, and one would hope tie the bottom end in with your rebar, but it doesn't always happen that way. We explored a variety of different meshes to see what would be a reasonable set of details to test in the laboratory. And what we found was that there was a strong correlation between the volume ratio of transverse steel that was applied and what was the peak strength in the experiment. We selected one of these to explore in the laboratory and just finished the test results on that within the last month. And here is the detail of the test specimen. And we explored two different geometries for the layout of the candy cane bars. In one layout, we put the candy cane bars only close to where the failure cone would initiate. So we were sure that these additional shear reinforcing bars would intersect the failure cone and be well developed on either side of that failure cone. We also, perhaps not trusting our finite element model results fully, and also not really knowing, not wanting to have a failure that extended beyond this curtailment of the candy cane bars. We also explored on the other side, extending these candy cane shear reinforcements out an additional 2 layers. We checked with the local engineers about whether we should put these candy cane bars inside the joint. And they said if they were designing the joint, they would use them, go ahead and put them in. So that's what we did. So here's the layout in plan for the shear reinforcement. And I'll bet this video also doesn't work, but I'll give it a try. And it appears I can't get this video to work either. Eventually, though, we did get breakout failure in both directions, but at a significantly increased force capacity. This slide shows a comparison of the envelope for the case. Well, actually, it's the calculated monotonic behavior for the case with no shear reinforcement, and the result that we obtained both analytically, the yellowish curves, and experimentally the gray and the black curves as shown here. So the shear reinforcement was quite effective in increasing the strength, as well as increasing the deformation capacity. John Silva won a bet with me. It turns out that in terms of strength and almost deformation capacity, 2 rows of the candy cane bars was just as good as 4 rows. And so I think we learned something there about where to place these bars to achieve maximum effect. This is a work in progress, and we're considering what our next steps are going to be at this time. But we do have some conclusions we'd like to share. First and foremost is the obvious one that breakout failure may govern the behavior of typical column foundation connections. Even if the headed bars are anchored farther than D over 1.5 into the connection, as ACI 318 says is safe to do. A basic question here is whether this same bullet point applies in the case where you have hooked bars. And I suspect that it does. But there are some experiments that are being planned in Taiwan right now to explore how similar connections would work if they had hook bars instead of these anchor bolts. Second bullet point, we also believe that this flexural compression factor C sub m removes some of the conservatism from the breakout equations and might be considered in ACI 318 in this next code cycle. Third point, the slab shear reinforcement is quite effective in improving both the strength and the ductility of these connections, and is a very useful way, an economical way to avoid having to significantly increase the depth of the footing when using these headed anchors. And finally, I wanted to point out that there is a fundamental inconsistency in the treatment of anchors and the treatment of hooked or headed reinforcement. And this lies in the use of the 5 percentile strength number versus something closer to a median strength number. If we're going to use the anchoring to concrete provisions that are in chapter 17, we should have a way of making the strengths more consistent philosophically with the strengths that we use for straight development length, for lap splices, for hooked bars and headed bars. And with that, Remy, I think I'll stop and take any questions that might have come up.
Thank you, Jack. There was one in the Q&A. I don't know if you can see that or I can read it.
Let's see. It says, how will the column axial load impact the design? So the column axial load would certainly change the flexural tension that would be associated with the problem. So that would be a clear effect. I don't think fundamentally it would have a big impact on the overall behavior of the connection. The interaction between the flexural tension in the anchor bolts and the flexural compression, that would change somewhat. But because the failure mode is really constrained to be within that zone anyway, I don't think it would have a big effect.
I suppose in the weird case that you had uplift on the column jack and moment at the same time, that effect that we count on with this psi sub m factor would probably go away.
It could, yeah. If you pull that, if you've got tension, which is an interesting case unto itself, that could impact how you use the psi sub m. But those are things that would need to be considered in a 318 code change proposal if one is put forward.
Mm-hmm. Jack, before I introduce John again, could I ask, do you have a sense for how one would provision these candy cane bars? How much is enough?
How much is enough?
Yeah, what area do I need?
Yeah, well, that's a subject we're working on at this time. One thought is to treat this as a punching shear type problem. Mm-hmm. And we have provisions available for shear and moment transfer in two-way slabs that have shear reinforcement, and quite likely that a similar provision as that would apply here. And so, I think there's a trade-off between how thick you make the connection and how much shear reinforcement you need. But I think the design is one that the designer's got a couple options to play with. One being the thickness of the footing, and the other being the amount of the candy cane bars. The extent of the candy cane bars seems to be pretty well delineated by being essentially within the depth of located with a perimeter equal to the depth of the connection. We looked at that analytically, and the Athena results suggested that I think having the candy cane bars within about 3/4 of the effective depth was sufficient. But I didn't trust the analytical results enough to not try extending them a longer distance on one side.
Sure.
There's other questions. Were there strains and candy cane bars measured? Absolutely. So we know which ones were effective, and it's the ones that were close in that really worked. On slide 10, the east and west breakout cone size was different. Why? I always chalked it up to just the variability of concrete. I don't know really why they were different. The outer extent of that breakout cone that you see is largely controlled not by the cone itself, but by how the top mat of reinforcement strips out of the top of the slab when the final failure breaks through. So it's a little bit misleading, I think, to take that outer zone as the definition of it.
Jack, thank you very much.
Bet.